Thanks very much, Julia. I'm excited to have this conversation today. So this kind of came out of our discussions in the spring about all the hype around hydrogen and questions about, is this the real deal? And we've talked about hydrogen a few times over the past few decades as potentially playing a big role in our energy future, and lots of questions still remaining. And so I've sort of targeted this as a bit of a hydrogen 101 from a carbon footprint perspective. This is an accumulation of information that we've pulled together with a few different collaborators. Most of it has not been published yet, and so it's still sort of ripe for feedback and questions and things like that. And I think my biggest message out of this is that it's a complex story, right? Talking about hydrogen and the potential role it could play is not something that's really easy to say it's good or it's bad. It needs the nuance to understand the details to make better decisions. And so my goal is to provide some of that detail for the purposes of having some of that conversation. But as I said, this is still a work in progress. And so I want to make sure that I'm not losing you because I've got lots of charts and things like that. And so please do just unmute and jump in if something's not clear. And we can sort of work through that as we go, and happy to keep it a bit informal in terms of jumping in with questions as we go as well. So for those of you that don't know me, I'm Jule Bergerson. I'm an associate professor in chemical and petroleum engineering at the University of Calgary and the Canada Research Chair in Energy Technology Assessment. So my group focuses on building and applying tools to assess technologies. And a lot of the work we do is trying to assess those technologies earlier in their development, because that's where you basically lock in most of your environmental impacts is at the design stage. And so modifying tools that were meant for commercial sort of applications to look at them earlier in the process, we might be able to avert some of the unintended consequences that come from new technologies, as well as help drive that innovation process. So make it happen more efficiently and effectively in that process. And so my sort of interest in hydrogen comes from that perspective in terms of there's a multitude of technologies and therefore footprints, plural, that you could actually derive from these hydrogen pathways. And so how do we investigate those and inform decisions about them? And so, as I said, this really comes about with the pressure to reduce greenhouse gas emissions everywhere, right? And following the COP26 discussions, and yesterday was an announcement about reducing greenhouse gas emissions in the healthcare sector, right? It touches every economic sector in every economy in terms of this pressure to reduce your greenhouse gas emissions. Hydrogen has the potential to reduce emissions in multiple sectors of the economy, and that adds some complexity and some questions about that. And we really don't have a full picture right now in terms of the magnitude of the system-wide impacts. So not just combusting the hydrogen for power production, for example, that has no emissions, that's great, but what about the rest of the system? And so taking that systems perspective is important. As well as with this multitude of options, how do we sort of apply them optimally? And in keeping with the ABINet sort of focus in terms of thinking about these transitions being very regional. And so looking for the opportunities to get your biggest bang for your buck at a regional scale, because those regional details are really important. And so I'm going to go through a few things today. So the first thing is, how do we today use hydrogen? And then how could we use hydrogen into the future? So looking at those potential applications and technologies. And then step through some work that we've done just to collect information about the carbon footprint associated with different hydrogen options, as well as the competitors to those hydrogen options that are being put forward. And then specifically talk about what's called blue hydrogen, because that is also a hot topic, and specifically in Alberta, it's a very, it's talked about quite a bit in terms of one of the big focus areas of deploying a hydrogen strategy. Just to step back quickly, for those of you that aren't familiar with life cycle assessment, this is the example I always give to give you a sense of what I mean when I say taking a systems perspective and looking at the life cycle details. And so this was back in 2009 or so, was another wave of EVs, and we've seen that grow exponentially since then. But even at the time that these new versions of electric vehicles were introduced into the market, there was a lot of questions, right? And a lot of debate about the role they could or should play, and then what some of the unintended consequences are in terms of the effects that they might have on the economy and on the environment. And so even back to the 1990s, when there was another surge in thinking about electric vehicles, California actually set a policy goal of reducing the local air quality pollution issues that they were having in the LA basin by encouraging the adoption of what they called zero emission vehicles into 3% of the fleet by 1998, and then set a future target of 10% by 2003. And so the idea with these is that they'd be fully battery powered. And so they had no tailpipes whatsoever. So no emissions at the point of use, which sounded great. But there was a study that was done that sort of showed that this implementation of these technologies wouldn't necessarily achieve the policy goals that were set. And I use this in my classes to introduce LCA. So I would ask you normally, what are the problems with this target for a policy goal? And the idea is that you have to think about the full life cycle perspective, right? And so this is the way that we define life cycle assessment is that it's a decision-making tool that helps you to structure the way you think about complex environmental issues. So identifying environmental burdens and evaluating the environmental consequences of either a product, process, or service over its entire life cycle, or what we call from cradle to grave. So cradle would be this material extraction at the top of the figure. You then got manufacturing, processing, production, some transport that's usually involved, and then using the final product, process, or service, and then the fate of the unwanted residuals and accounting for all of that. And so from an engineering perspective, we would think about this as a very large mass and energy balance on the system. So really tracking all the inputs and all the outputs associated with each of the stages of the supply chain, and then balancing that to make sure you're accounting for all the mass and energy that's associated with this. And so with that, we can take that bigger picture approach to understand that. And when it comes to the EV example, two of the major things that they had sort of not taken into account with that policy was the fact that California was importing a lot of coal-fired electricity from neighboring states. And so while you might improve the local air quality in the LA basin, you're going to shift pollution to happen in other parts of the US. And so you're creating new environmental problems even by fixing the one. And then perhaps the more important one was at the time in the 90s, they were using lead acid batteries for their electric vehicles. And that lead didn't have a recycling process. And so that study that was done actually identified that there was going to be more lead introduced into the environment than if you had actually burned leaded gasoline, which they had just banned in California. So again, this idea that helping to assess these kind of policies and technologies can help you to understand what potential unintended consequences you might have associated with implementing a technology or a policy. But more so, you could actually feed that back into alternative policies and technologies that could actually help to achieve the air quality goal without compromising other aspects of the economy or the environment. And so that's sort of the concept of life cycle assessment and a type of application that you could use it for. So let's think about that in terms of hydrogen. And so I'm assuming that most of you have heard the discussion about hydrogen in terms of their colors. And so these are the three main colors that are talked about when we talk about hydrogen. And really what it means is a differentiation about the production of the hydrogen. So how do you derive the hydrogen product that you could use for multiple purposes? And so on the left-hand side is the green hydrogen. That's where you would use renewable electricity to actually split water, right? So the hydrogen source would be the water itself, and you'd use electricity that comes from a renewable or low carbon source to produce that hydrogen through electrolysis, right? On the other side is the gray hydrogen. That's where you would use a fossil fuel type, and primarily we use natural gas today to produce hydrogen. And we would actually convert that, right, by putting it through what's called a steam methane reformer to actually split the hydrogen away from the methane molecule. And what you end up with is carbon that gets oxidized and is released to the atmosphere as CO2, right? So that's what's considered to be gray hydrogen. And then in between is what's called blue hydrogen. So blue hydrogen is where you're still using that natural gas. And in many cases, you're still using the steam methane reformer to actually break apart the methane molecule. But instead of actually venting that CO2 to the atmosphere, you actually capture that CO2 and either convert it into some other product, or you actually pump it underground and store it in something like a saline aquifer so that that CO2 doesn't enter into the atmosphere. And so those are the main colors that are talked about when it comes to hydrogen. But in actual fact, there is a huge spectrum and people really get caught up in these definitions. Looking through this, you can see different types of definitions of different colors. The gray typically is the natural gas system, and then it's blue if you capture the carbon. The brown or black is coal, different types of coal and oil. Turquoise would be natural gas with just a different conversion process. The purple and the pink would be like the green, except that it's using nuclear power and it's using it in two different ways. White, there's different sources will use white for different purposes, but oftentimes it's something where it's a byproduct that comes out of an existing industrial facility, for example. And so, there's a lot of the hype is focused around determining which color your hydrogen is. And I think that that's, largely unproductive in terms of defining this, both because there's a range of possible greenhouse gas emissions you could get for each of these colors, but also that it is only focused on the way you produce hydrogen and not on the way you could actually make use of it, transport it, store it, all of those kind of things. So it really doesn't take that systems perspective into account, which I think is really important. And so to do that, we have to sort of start thinking about each of the supply chain steps. So this would be the life cycle pathway of hydrogen. And so you start by the hydrogen containing substances on the left-hand side, right? So where is your source of hydrogen going to come from? You then go through some sort of transformation process because we don't have hydrogen sitting readily available in the form that we want to use it. So there's some sort of transformation or production process that needs to occur. Then you need to think about how you transport that and store it, and then actually use it for some purpose, right? And that's the sort of systems perspective. If the hydrogen is the source of the hydrogen that you want to use actually comes from water, then you need to think about electricity production as well. So you need to actually feed that electrolysis process with electricity in addition to that water. And so you also have to think about where does that electricity come from, right? And so with the EV example that I gave earlier, importing coal-fired electricity from a neighboring state sort of, diminishes the benefit you might get from the fact that burning hydrogen in a vehicle has zero carbon emissions. So along with the hype, there's a hydrogen strategy for just about every jurisdiction I've seen. And so the federal government in Canada has a hydrogen strategy, seizing the opportunities for hydrogen. And the link is there if you want to look at some of the details. I think what's important here is both Canada and Alberta just recently announced their hydrogen strategy. And with both of them, they really do try to de-emphasize the color coding of these things and really try to focus on the actual carbon intensity of each of these products to make sure that we're actually looking for the low carbon options. With the federal program, they have some targets that they've set, and you can see that they've got a range of different ways that they hope to develop an economy around hydrogen. So looking for use in passenger vehicles, so fuel cell electric vehicles, also using it for a range of different industrial applications and things like that. And you can see that they've got it tied into the energy system of the future for Canada, as well as showing that we're one of the top 3 global clean hydrogen producers in the world. They've tied it to revenue that they hope to get, as well as jobs, in addition to the CO2 emission reductions that they hope to see. And so with that, they do recognize the fact that like everything else in our energy system, our energy systems are extremely regional in Canada. So even though we have a relatively small population, our energy systems look very different from one province to the next. And so here they've got the strategy, and you can see that they've actually acknowledged that there are different options for producing that hydrogen, as well as different end uses where you could actually make use of that hydrogen. And then they've actually laid it out for what they suspect would be the sort of midpoint, sort of production and end use that would be targeted for each of the provinces and territories throughout Canada. And so this just acknowledges that there's both the differences on the production side, which would be where you get that color coding, as well as acknowledging that the downstream end use part of the supply chain is also important to think about, and that it's diverse across Canada. So just last week, actually, Alberta announced its own hydrogen strategy. So they did have they had a natural gas strategy that they announced last year. Last week, they announced what they called the hydrogen roadmap. So this was a targeted plan for how to get hydrogen within the Alberta context. And with that one, you can see that they've also tried to not differentiate based on color, but by carbon intensity. And then the actual applications are a little bit different in the balance of where they're going to focus their efforts, but they're seeing that hydrogen could be used in heating, both for residential and commercial applications, for power generation and storage. They also focus on exports, which the federal government hasn't really focused on. So they are promoting the fact that you could actually produce hydrogen in Alberta and actually ship it overseas to compete in other jurisdictions around the world. Hydrogen for transportation, and then industrial processes as well. And the industrial process part is really where Alberta actually has a strategic advantage, and we produce the most hydrogen in the country for use in industrial processes like the upgrading and refining activities that happen in Alberta. And so really trying to leverage that, as well as our plentiful, cheap natural gas. The other thing that's interesting about the Alberta plan is that they're actually targeting the carbon intensity. So this is kilograms of CO2 per kilogram of hydrogen that is produced, right? That's the carbon intensity. And so they've got a few example cases of different ways in which you could provide that hydrogen. And then they're also adopting Europe's first guarantee of origin for low carbon hydrogen. And so this is something that we see developing. I'd say it's still in its infancy and there's still some things to work out, but this Certify project is really trying to set the bar of, if you call it low carbon, it should be below this intensity threshold. And so what they've set is the 4.37 kilograms of CO2 per kilogram of hydrogen. And what you can see here is that there's different combinations. So the left two bars are renewably based hydrogen sources. So one thing to point out is that even if you use wind power to generate your electrolysis process, that doesn't mean that it's a net neutral or a net zero source of hydrogen, right? Every supply chain and industrial process does have CO2 emissions associated with them. The biomass derived hydrogen, so this is a very specific gasification and pyrolysis option, could also be below that threshold, but would be higher in emissions than the wind. And then the three on the right are different fossil-based systems that could potentially compete or not with that threshold of what you would define as low. And I wouldn't get fixated on these numbers. I think that these numbers are very specific cases, and I'll show you some other examples as well. But just to note that there are some fossil-based pathways that would be below that threshold and some that would be above. So what I wanted to do now is just show you some of the work that I've done in collaboration with JT Luderbach, who was an undergraduate engineering summer student in my group over the past summer, Amar Haider, who just recently graduated from our undergraduate program, and then Dr. Sylvia Sleep, who was a postdoc when we started this work and has just recently taken on a faculty position in civil engineering at the University of Calgary. So I'll just plug that she could potentially be another ABINET member coming up, and just getting started in that position. But the three of them and myself worked together to sort of just try to pull together what was happening in the literature in terms of estimating these emissions. And so I'm going to do my best to show you this. This is something that Amar put together to try and just help visualize this. And so this is just a sort of looking at that supply chain where you look at the extraction of hydrogen or production of hydrogen all the way through to its end use. And so these are the hydrogen sources at the bottom. Then you process them, produce the hydrogen, you have to transport and or store, and then you have different uses. So I'll just go through quickly the hydrogen sources themselves. There is a multitude of ways that you could actually produce hydrogen. So all of these different options have the ability to produce hydrogen, either directly because there is hydrogen within the fossil options themselves, or by using something like biomass or photovoltaic solar to generate electricity that could then split the water to create that hydrogen. So a wide range of these, and then whether or not you put carbon capture and storage onto the fossil-based system and even the biomass system could dictate the overall carbon footprint of doing that. And so if we move to the conversion technologies, there's also a range of different ways you could actually produce that hydrogen. So the green hydrogen side, that electrolysis process is the same. It's just the source of electricity that you use to fuel that. On the fossil and the biomass side, there's gasification, pyrolysis, and then the thermal reforming or the steam methane reforming for the natural gas system. And so this white natural gas steam methane reforming is the incumbent technology. The vast majority of hydrogen that's produced around the world is uses natural gas through the steam methane reforming process. So once you have that hydrogen, you need to then think about transport. And there's a range of different options for that transport step. By road, by rail, by sea, in a dedicated hydrogen pipeline. We've also talked in Alberta about spiking a natural gas pipeline. So the majority of what would flow through the pipeline would be natural gas. gas, it would just have a higher hydrogen content than you normally would, right? So you can slowly start offsetting the emissions associated with natural gas by having some of that fuel that goes into something like a power plant be replaced by hydrogen, which wouldn't result in combustion emissions. When we think about the uses, these are major sectors of the Canadian economy as an example. And on the bottom, they've been ranked from highest to lowest in terms of their magnitude of greenhouse gas emissions in the year 2020. So you can see transport, of the sectors where it's possible to make use of hydrogen, transport has the largest opportunity in terms of it contributing 186 megatons of CO2 equivalent. And that is in the context of over 700 megatons for Canada as a whole. And so the next option would be power generation. So even though we use the majority of our electricity comes from hydropower in Canada, we still have 61 megatons coming from the combustion of coal, natural gas, and other. Space heating is next. Steel production, the petroleum refining, and the just zoom in here. The petroleum refining is where we actually produce and use most of the hydrogen in Canada today. And so we have refinery fuel gas that we can reform into hydrogen. We can take natural gas and reform that through the steam methane reformer. And then we have an option of potentially looking at that petroleum coke that's produced as well. This one is the ammonia production. So that's the second largest source of hydrogen consumption in Canada today. And you can see that the vast majority of that is actually produced using natural gas. So another opportunity to either grow that or replace the means by which we actually produce that hydrogen. Cement production as well. Some of these are a little bit more complicated in terms of where the source of their greenhouse gas emissions are and what the options are to replace what's currently being used with something like hydrogen. So this requires more investigation in terms of where do you get the biggest bang for your buck in terms of the reductions that you're seeking, right? And so transportation looks like the biggest because it's the absolute largest contributor to greenhouse gas emissions of the sectors that could use hydrogen. But how difficult it is to replace something like an internal combustion engine or its competitor, the electric vehicle, is some of the questions that we want to get at with this research. Okay. So going back to our life cycle diagram then, as we said, you have the hydrogen containing substances, the production, transport, storage, and consumption. So when we think about electricity production, then we have to think about all of the different sources that we could use to generate that electricity. Through the production process, we've got a lot of different chemical conversions that could possibly occur. And so this is helping to show some of the complexity, right? These are the ways in which we could produce hydrogen. How do we assess which of these is going to be the optimal one for a particular region? The transport options, distance and locations are going to be important. I think it's important to say that, if it's going to go overseas, we have to use something like a tanker ship. And while that is the focus of the, one of the areas of focus for the Alberta strategy, at last search, we could only find one operating hydrogen tanker in the world operating today, and it was just about to be operated in the last year when I had students looking into this. And so that's something that is possible, but needs additional investigation. The hydrogen storage side, you could use pressurized tanks, you could use underground pore storage. You could also do this, use of that to deal with intermittency in the electricity system, for example. And then you have all the multitude. So this even goes beyond the ones that I have shown in terms of Canada's drivers of greenhouse gas emissions, to think about the ways in which you could use hydrogen to reduce greenhouse gas emissions. And so this is some of the complexity. So actually quantifying the greenhouse gas emissions associated with each of these pathways would be required. And then understanding how it might be different if you did this in Alberta versus Bavaria is the next question, right? What are the regional differences and how do those affect the carbon footprint of each of these pathways? Excuse me. So the upstream process is where most people start, right? Where the color coding started and where we start by making those comparisons. And the argument has been made that the downstream processes don't actually emit CO2 themselves, right? In the combustion of CO2, for example. And so why do you need to look at that? Really, the big driver is the upstream. And I'll talk a little bit more about why that's too simplistic for decision making, but we'll start with characterizing those upstream processes. And so this is the beginning of many of these bar charts. So please ask if there's anything that's unclear. This is looking at just the upstream processes to produce that hydrogen. And it's greenhouse gas emissions, so kilograms of CO2 equivalent per kilogram of hydrogen that's produced, right? And what we see, the red outline is the steam methane reforming using natural gas, which is what we do today. And then the other gray options, we're actually combining coal, oil, and natural gas together as gray to be the fossil options that you could have to produce hydrogen. You can see that with coal gasification, the next bar, you're more than double the emissions than what we're doing today. With oil, partial oxidation and other processes, you could be just a little bit lower than the steam methane reforming. And then the autothermal reforming, a slight variant and a slightly more efficient way to produce that hydrogen could reduce your emissions ever so slightly. The other one that is tough to put into a category, so we put it into gray because we're saying that we're going to use water electrolysis, but we're going to do that using a grid intensity. So the average electron that comes in to an electrolysis process can actually, introduce more carbon into the atmosphere than what we're doing today. And so that's why we considered it to be a gray option. If we actually think about some of the blue and turquoise is just basically just a different process of producing it. But these are options to continue to use fossil, but to actually put carbon capture and storage on that in order to reduce the emissions below what we're doing today. So that incumbent, which is the SMR red. And so what you can see is that if you do it well, you can actually reduce the emissions quite a bit below, right? So with a ATR with carbon capture and storage, you can be at 1.6 kilograms of CO2 equivalent per kilogram of hydrogen, which is almost a 10-fold reduction in your greenhouse gas emissions, right? This is just on the production side. So there are opportunities to lower the footprint using a blue hydrogen option. The green options also vary. So depending on, you can do the water electrolysis, but you can do it with different forms of electricity. And you can see that that will result in much lower emissions as well, but different levels of emissions depending on the source of the hydrogen itself. You can also see that the biomass option, so this is biomass gasification with carbon capture and storage, that is actually the only option that actually allows you to get to a negative emission space. So the fact that you are absorbing the CO2 by growing the biomass, and then when you combust that, normally that would go back into the atmosphere. So you'd be close to net neutral. In this case, if you put carbon capture and storage on that biomass facility, you actually end up with negative emissions. That's possible. There are other details because this isn't the full life cycle. This is just the production process, but it is technically possible to get negative emissions using biomass for that hydrogen production. Okay, so that's the range of different options on the upstream side. And so you can see that the story is quite complicated. The last thing I'll say on this is just that we do have a range of options. So the whiskers that are there are starting to take some of that variability that we see in the literature into account. And you can see that even one option can vary, by an order of 5 kilograms of CO2 per kilogram of hydrogen, just based on the way you implement it, the other energy sources that are used in the upstream process, those kinds of things, right? So quite a bit of variability here. And if we complicate it further by looking at the full life cycle, right? So now we're not just looking at the upstream process of producing that hydrogen, but we're also looking at the steps that happen downstream to actually deliver an energy service that we want. So this example is for transportation. So if we're using a fuel cell electric vehicle instead of an internal combustion engine, or instead of an electric vehicle, a battery vehicle, then we can actually use this for transportation. Right. So looking at that carbon footprint, one of the reasons why this is important is because we need to know if we're doing better than what we're doing today. Right. So we saw that the steam methane reformer, we could compare the upstream options to what we're doing today to see if we're better off or worse off. And so we want to do the same thing for this. And so we start actually with the incumbent technology, right? So an internal combustion engine vehicle. And you can see here, these are the life cycle or cradle to grave CO2 emissions. So again, CO2 equivalent per kilometer traveled. And so we've got the different stages of the life cycle presented here. So you've got the blue is the production of the gasoline itself. You've got the gray, which is the vehicle manufacturing. And then you've got the yellow, which is actually the use phase. So actually combusting the gasoline in the vehicle to drive 1 kilometer. right? So the effect is that the life cycle emissions of an internal combustion engine powered by gasoline is that it's 263 grams of CO2 that are emitted for every kilometer that's traveled, right? If we then look at a competitor to hydrogen for transportation, we could look at a battery electric vehicle, right? So this is a full electric vehicle. And what you can see is that the life cycle emissions, we don't have use phase emissions because we're not combusting anything at the point of use. You can see that the vehicle manufacturing emissions go up. So it is more greenhouse gas intensive to produce an electric vehicle. And then we can also see that depending on where you operate that vehicle, the electricity that you're using can actually have very different greenhouse gas emissions, right? So in Canada, as an average, we use over 60% of our electricity is produced using hydropower. So that's going to be a lot less emission intensive than in Alberta, where we use natural gas and coal. Right? BC has a very low emission intensity because it's almost all hydroelectricity. And so the emissions associated with an electric vehicle in BC are quite a bit smaller than in Alberta. And I would say I've been watching this because we're sort of decarbonizing and using our coal plants less. And so this impact of Alberta has been going down over time, and we expect it to continue to go down over time. And so we've just sort of hit that threshold that it actually makes more sense to drive an electric vehicle in Alberta than it does to drive an internal combustion engine, but just past that threshold when you're looking just at the carbon footprint associated with that. And so these are the pathways that hydrogen has to compete against in terms of transportation if it's going to be a lower carbon option, right? And what we see is that when we look across all the different colors and all the different options that we could use, these are using a fuel cell electric vehicle, you can see that the numbers vary pretty considerably, right? But we can see that the emissions associated even with renewably based electrolysis processes have a tough time competing against electric vehicles with a low carbon grid. Right? So in Alberta, it would be better to do renewable electricity with a fuel cell vehicle right now. But in BC, it would actually be better to do an electric vehicle. Maybe I'll just pause there because there's a lot of data there. Is there any questions about following the bar charts here?
Well, maybe if you produce the hydrogen in Alberta, then the budget. I would wish to see one of the bars also for the production of the hydrogen in Alberta with Albertan power. So and that's a reality. So the electrolyzers do normally not run on photovoltaics. They run on the power mix from the individual provinces. And that makes a huge difference for the hydrogen story.
Yeah, very, very good point. Thank you, Jürgen. So you can see here in the far right of the gray section that we have water electrolysis using the EU grid. This was from a study that was done. And so you can be much, much worse using high carbon intensive electricity. So that's a good point, that if you have cheap and plentiful renewable electricity, the electric vehicle will win. If you're using high carbon intensive electricity, it's not going to compete under these circumstances. Yes. Yeah, so that's a good proxy for the Alberta system here. Great. Okay. So then looking at the use of it for electricity, right? So this is where we have a multitude, and I'm not going to go through every single sector. I do have a figure for those if you're interested in something that I'm not mentioning, but I just thought I'd contrast this with electricity. So using the hydrogen for producing electricity, looking at that full life cycle and comparing it to the incumbents that you would need to compete against in order to see whether it was actually lower carbon. So in this case, we're looking at grams of CO2 equivalent, this time per kilowatt hour of electricity that you could consume. And so here we're looking at a few different aspects. So the ones that have the bars around them, those are the incumbents. So this would be without hydrogen. This would just be using natural gas, for example, at 442. So if you're combusting natural gas in a combined cycle unit to produce electricity, you would end up with 442 grams of CO2 equivalent per kilowatt hour electric. And then you can compare that to actually converting natural gas into hydrogen and then combusting that hydrogen for power production. And so that would bump you up actually, right? And so we see that for most of these, where if you're just shifting from burning the fuel that you originally had for power production versus adding a step to convert that to hydrogen, you're not going to get a greenhouse gas emission benefit, right? And that's the second law of thermodynamics, that you can convert energy from one form to the other, but you get losses along the way. And so then you look at the options for converting that, but with carbon capture and storage, or with water electrolysis using a renewable source. And so again, you can see that you can do better than what we're doing today using these options, but that there is quite a bit of variability in terms of the overall carbon footprint associated with these. Okay, so a similar story. I do have other options for this power production as well. They just wouldn't all fit on one figure. So I've just got this on the next figure here, still trying to compare against this natural gas-based power production, which is the vast majority of how we generate our power in Alberta now. So you could use hydroelectricity, biomass. And then on the right-hand side, I just give you some examples of the grid intensity in different regions of Canada. So again, Canada, this 790 is a few years old now. We're down to about 650 or so. But, you know, these options than that grid average. But again, hard to compete with BC with mostly hydropower. Right. So again, the context of the region in which you're actually deploying these and what you're going to be offsetting by deploying hydrogen-based electricity versus something else. The last point I would say is just that idea that a lot of the discussion now is how do you actually incrementally offset some of the stuff that we have already? So making use of an existing natural gas power plant and pipeline, by introducing some hydrogen into that, you can actually get somewhere between the natural gas emissions that we have today and something like the SMR with carbon capture and storage. So you can start seeing reductions without a significant investment in infrastructure other than the carbon capture piece. And so you can start seeing those reductions, but not as competitive as something like hydropower with water electrolysis. Right, so it helps to give you that sense of the relative magnitude of the reductions that you could see. Okay, so one thing I wanted to delve into in a little bit more detail is looking at blue hydrogen specifically, right? So this is natural gas for hydrogen production. And there's been quite a bit of discussion. There was a paper that ended up being cited in the New York Times talking about how blue hydrogen was worse than coal for different applications and things like that. And so this group of researchers from a range of different organizations, we had gotten together to sort of look at, you know, what are the differences in the ways in which you could produce hydrogen using natural gas, and what sort of insights could we get in terms of recommending ways in which that could work well versus not. So this is just a preprint. We're in revisions and have resubmitted those revisions. But because the conversation is going on right now, we wanted to get this out as a preprint. So these are looking at kilograms of CO2 equivalent per megajoule of hydrogen that's produced, but it looks at the full life cycle. So here we're looking at the CO2 fuel chain for the CO2, the fuel supply chain for the system, and the CO2 emissions versus the methane emissions. We have the direct CO2 emissions, the electricity that you would use from the grid, and other sources of emissions you would see across that life cycle. So these are different options, and they're all associated with blue hydrogen. So it's taking that whisker of variability and starting to unpack that to understand more about what are the drivers of being at the high side of these emissions versus the low side of these emissions. And so you can see we've got three groupings here. And one of the big factors is how much methane gets into the atmosphere because you have produced the natural gas that's used for hydrogen production. And that data is actually still not all that robust around the world. We have seen that there are sort of really big sites where a leakage is happening that hasn't been detected, and huge volumes of methane get into the atmosphere. Because methane has a higher impact on the climate, every molecule of methane has an impact that is higher than a molecule of CO2. It has a magnifying effect for any ton of methane that you release. You're going to have a bigger impact on the climate, and that's something that is really important to take into account. And then if you have a leaky system so that you're actually losing a bunch of the methane that normally you would use to convert to hydrogen, you can actually change the results pretty considerably. So in this case, this is just basically a sensitivity analysis. So if you get an emission rate of methane throughout your supply chain of 0.2%, then the first 6 bars are relevant. right? If that methane that you're producing actually jumps up to a leakage rate of 1.5%, then you have the middle 6 bars. If that rate is at 8%, and there are pathways we've seen at 8%, then your emissions actually are, orders of magnitude larger. And so that's a really big driver of the overall impact of a blue hydrogen supply chain, is how integrated is that supply chain and how well is it managed in terms of the methane that could be leaking. And we see leakage from the actual wellheads themselves through the pipelines. Every step of that supply chain has potential leakages associated with that. I would say Canada is actually at the lower end of this leakage rate. We actually have pretty good methods and best practices that have been implemented to detect and mitigate that, but it's still a concern. And part of the problem is that you don't see this methane leaking. And so unless you're having thorough investigation campaigns to actually detect this and then fix it, you can miss some of this. And so we see around the world that this methane can be a pretty significant issue. The other part is that if you're putting carbon capture and storage on, it can have an effect. So if we look at the low emission rate of 0.2% on the left side, you can have the greenhouse gas emissions if you do not have carbon capture and storage, are the first 2 bars. If you capture 55% of the CO2 are the next 2. And then if you capture 93% of those emissions, you can see that you're decreasing your greenhouse gas emissions by almost an order of magnitude. And so that's important to think about, is that not only is it whether you put carbon capture or not on the system, it's how much of that CO2 are we actually capturing. And some of the implementation that we've seen of carbon capture is sort of a proof of concept and things like that. So they're actually not capturing the full suite of CO2 emissions that are coming from the plant. And so that's another piece that's really important to think about. The last piece is these global warming potential 100 versus 20. And these are the time horizons over which you look at the impact from methane releases. And so if you take a 20-year time horizon, methane doesn't last in the atmosphere as long as CO2, but it has a much bigger impact. And if we care about the emissions that are occurring in the next 20 years, then the 20-year time horizon is important to think about. If we want to think about the long-term impacts of these different decisions, then a 100-year time horizon is a better integrator for the global warming potential. And so both of these, I would argue, are important to think about. And in the 20-year time horizon, what you can see is if you have a high leakage rate of methane, then the impact of that methane in a 20-year time horizon is a lot bigger than if you take a 100-year time horizon and average those impacts over 100 years. And so the right-hand side shows you the magnitude of the difference if you take the 20-year versus the 100-year perspective. If you are getting a very small leakage rate of that methane, then it's less pronounced, that effect. And so you can see on the left-hand side that the two pairs of results, looking at the 20-year and 100-year, it's much less impactful which of those perspectives you take, right? So the end result is if you can reduce the methane emissions, you're going to have a much bigger impact on that, regardless of whether you take the 20-year or the 100-year time horizon. So just to summarize that from that paper then, is that blue hydrogen can produce a carbon solution, sorry, and I should have emphasized that. So the ideal case where you have 93% capture plus, right? You want to maximize the amount of CO2 you actually take out, regardless of whether you take a 20-year or a 100-year. If your methane leakage rate is low, right? If it's a well-managed supply chain, then you can deliver what we could consider a low carbon source of hydrogen, right? All the other options would be above that threshold that's been set, right? So there are ways to do hydrogen poorly, blue hydrogen poorly, and there are ways to do it well. And so it can produce a lower carbon solution, but again, it has to be compared to the incumbent and the competitors in a particular region before you conclude for sure that it's going to be a climate solution. If you want to focus on blue hydrogen, you really have to focus on that methane leakage, the state-of-the-art technologies with the highest capture rates that you can, and then doing energy and heat optimization. Also looking for the regions and applications where high carbon incumbent technologies are there, and that the competing technologies have either logistical or other issues in terms of deploying them. That global warming potential 20 versus 100-year is not necessarily something that you could resolve technically. It's more about taking both perspectives to make sure that you're finding solutions that will have the effect that we want in the short term as well as in that long term. And so my final thoughts then are just that, the prospect of hydrogen is a complicated story, and I've try to scratch the surface of some of the reasons why it's complex and why we need to take that systems perspective, right? It's not about just doing the color coding of the production options. It's also thinking about the ways in which it could be deployed and where it could be most effectively used. I think the other thing that comes out in looking at this material is that transparent public processes that assess and track carbon footprints are absolutely critical for society to support and acknowledge emission reductions that are occurring. Without that transparent system, even if you focus on the renewable electricity and electrolysis processes, I would argue that you need to get society to be on board with that type of investment and to track the emission reductions that are actually occurring. And so having open, transparent data that actually tracks that information is going to be critical to the success of any new technology that's trying to be deployed to reduce those emissions. Future work that we're looking at is to expand this, to look beyond carbon footprints, right? The carbon is top of mind and is something that we need to aggressively work on, but there are other potential unintended consequences that need to be taken into account. And obviously this needs to sit next to the economics of each of these pathways, because each of those are going to require different types of investment, different trade-offs between CapEx versus OpEx and those kinds of things. So we need to think about that more holistically than even what I've shown. Regionally specific applications and assessments are needed. So you need to actually get into the details of where would you deploy this, what would you offset, and those kinds of things. And then I would say, given the multitude of options, we really need to focus on the discussions of prioritizing the technologies and applications with that eye on the prize of getting the biggest bang for our buck in terms of reducing the maximum amount of CO2 emissions without other consequences and in the most efficient way possible. So with that, I thank you for following all of those many bar charts, and happy to take any questions or discussion at this point. Thank you.